Hello everyone, welcome to our channel. We are going to solve these physical metallurgy questions. First question is in the Eutectoid steel, which one of the following structures does not form during continuous cooling? Right? So what is the structure which is not forming during this continuous cooling? If you see the CCT graph, it is like this, right? So here fully pearlitic, yes, it can form. Then pearlite plus bainitic, it can also form, like some amount of bainite can be formed, but it is not that fully bainite will form, right? So this is the correct option, which is going to be not forming, like fully bainitic is not going to form. Yes, martensite can also form, yes, right? So this is the answer. Which one of the following is a ferrite stabilizer in steels? So ferrite stabilizer, that means ferrite is your BCC, right? So always you remember that a BCC is stabilized when we add another BCC, right? So here it is your chromium. It has got BCC structure and it is stabilizes this ferrite. Okay. Next, which one of the following expands upon solidification? That means when we do the solidification, that means we decrease the temperature, then the volume increases, right? Here normally the volume decreases for many cases, but here in one case it increases, and that is your gray cast iron. And why does it happen? Because once the gray cast iron forms, then it forms graphite, right? So graphite is nothing but a pure carbon, and relatively the volume of pure carbon, yes, is volume of is carbon is your greater than your Fe3C, like cementite, which was the earlier form. And normally in the steel, the carbon is present in the form of Fe3C. Okay, so this is the explanation. Next, for a simple cubic unit cell with unit vectors I, J, K, the angle between lattice vectors 1, 0, 0 and 1, 1, 1. So right, so these are some unit vectors. Okay, the angle between the vectors 1, 0, 0, right? So we can write it as 1i plus 0j plus 0k, right? Let us write this b vector as 1i plus 1j plus 1k, right? So what is the angle between them? To find that, we need to do this dot product. So it will be modulus of a modulus of b into cos theta. So a dot b will be 1 into 1 1 and I into I, that will be 1. Okay, so 0 and 0. So 1 is equal to mod 1 will be 1, mod a will be 1 and mod b will be your root over 3, right, to cos theta. So this implies cos theta will be equal to 1 divided by root 3. So this implies theta is equal to cos inverse 1 by root 3, and the value of this 1 by root 3 is 54.73. Okay, so option B is the correct answer. Let us move on. With the increase in the degree of supercooling, the growth rate of a nucleus follows which one of the following trends? Right, guys? So it is asking about this growth rate, right? If you see the diagram, okay, this is your temperature, okay, and this is the rate. Okay, so what happens? All the growth or nucleation happens below this melting point, right? So suppose this is your melting point. So what happens at melting point? There is no formation of any nuclei. It only happens, there is just drop of small amount of temperature, because that gives some extra energy for the formation of this nucleus. Okay, so what happens, and since the nuclei form and that is at high temperature, so diffusion rate is also very high, okay? So diffusion rate is higher, so that means the atomic movement. Like suppose there is a nucleus, right? It has formed, and in the surrounding there are atoms. So these atoms will quickly move to this. So it will help to increase the size of this. So that's why the growth will be higher, right? So that's why just near to melting point, just but it is below the melting point, the nucleation rate and the growth rate is high, and after that what happens, it decreases. Okay, so similar trend is observed for nucleation rate, then transformation rate also. Okay, okay guys, so this is the thing. So it first increases and then decreases. It is first increasing, then it is decreasing. Okay, so that is the correct answer. Next, for a FCC unit cell, the ratio of number of tetrahedral voids to the number of atoms. So it is asking about this tetrahedral. What is the total number of atoms in FCC? It is 4, right? And what is the number of tetrahedral void? It is 8. Okay, so it is 2 times, right? So that's why the ratio will be your 2:1. Okay, so in the case of FCC. Okay guys, now let us move on. The material in which there is conduction primarily by holes is. So when the conduction by holes takes place, then it is called as p-type semiconductor. That means positive, because hole is considered as hole is equal to positive. And why it is positive? Because it is assumed as absence of electron, and electron has negative charge. So if it is if there is no negative charge, that means there is positive charge. Okay, next, match the heat treatment process in group 1 with the resultant microstructures of steel in group 2. See, first is Mar tempering, right? Then normalizing, subcritical annealing for long time, full annealing. Okay, so what is formed in Mar tempering? First we will form this martensite, then we will do some tempering, so it will form tempered martensite. Okay, so P matches with your 3. Then we have normalizing. So in the case of normalizing, we get fine pearlite, we get somewhat finer size, right? Because the cooling rate is slightly higher as compared to annealing, right? Okay, then subcritical annealing for long time. Subcritical annealing, what is that? We know it is here 723 degrees centigrade. So this is your first critical line, that is AC1, and this is your AC3. Okay, so just below this AC1 we keep the sample for a very prolonged time. So what happens, the cementite which is there, like Fe3C which is there, so it becomes very larger size, right? So that's why we get spheroidized cementite in the matrix of ferrite. Okay, the last one is full annealing. So in the case of full annealing, we'll get this coarse pearlite. Okay, so this matches with option D, because P3, Q2, R4 and S1. Okay guys, no issue. Let us proceed. In case of homogeneous nucleation, the critical edge length for a cube-shaped nucleus is gamma, that is energy per unit area of the interface between the product and the parent phase. Delta J gives free energy change per unit volume. So this is asking for a nuclei which is of cube shape. How this cube shape looks like this, and the edge length is A, right? For the cube, we know what is the volume. Volume is A cube. What is your surface area? It is 6A square, right? Why we have written this? Because we know the formula to find this delta G, this complete delta G, that is equal to gamma surface into area, right? So area of surface plus this delta G, that is per unit volume, into this volume, right? So it will be gamma S into area is 6a square, and it will be delta G, and the volume will be a cube, right? So now to find this critical edge length, right, what is the size?
Here's what I found.
Okay, then we need to differentiate it. So delta A by delta A, it will be, so it will be 12a gamma s plus 3a square delta G. So now we will have to equate it with 0, right? So it will be 12a gamma s is equal to minus 3a square delta G. Okay, so del A, so from this A will be your 4 gamma s by delta G with negative sign. Okay, so this will give you the critical one. That means when we have this edge length, the delta G is at the maximum, right? So you can check also. First you will have to double differentiate it, and after that you put this value, then you will come to know that delta G at that point is the maximum, that is the critical to be reached. Okay, so it is option A basically, right? Should I check this one that it is really the maximum value? Yes, you can check. So let us again differentiate this delta E by delta S square. So what will be it? It will be 12 gamma S plus 6A to delta G. Okay, so let us put this one. 6 into A minus 4 gamma S by delta G to delta G. Okay, so it will be 12 gamma S minus 24 gamma S, so it will be minus 12 gamma S. So this value is negative, so once this double differentiation is negative, that means the value which is there, it will be maximum, right? This is for the maximum condition. Okay, hence it is proved also. Let us move. For a cubic metal with lattice parameter of 3.92 angstrom, the first 4 diffraction peaks from the X-ray powder diffraction patterns taken with copper K alpha radiation lambda is equal to 1.5405 angstrom occurs at 2 theta values of 39.7, 46.2, 67.5, 81.3. The crystal structure of the material of this metal is. Okay, so guys, I think you must have solved this type of problem. So I will tell you the method to solve this type. Now suppose the diffraction happens at different angles, right? Like this. Okay, different angles. So what are the angles here? Suppose these are like 39.7, then 46.2, 67.5 and 81.3. So these are all 2 theta values, right? So you will have to write this one like this, 2 theta values. You write it first. So it is 39.7, 46.2, 67.5, 81.3. Then you will have to write theta, right? So theta, you do it. Then you will have to write your sine theta. Okay, so guys, you can write this theta by your own. I am writing this sine theta, so it is like 0.33, 0.39, 0.55, 0.65, right? The next step will be to find this sine square theta. Okay, the sine square theta will be 0.1089, 0.1521, 0.3025, and 0.4225. After that, this is the important step, right? So whatever the first value which is there, right, this is your first value, so we will have to divide all the values with the first value, right? So like we can say we are going to find sine square theta divided by the first value, that is 0.1089. So it will be like 1, then 1.39, then 2.77, then 3.87, right? So these are the things. Now the next step is to convert this into integer, and if it is follows the pattern, like for BCC we know it is like 2, 4, 6, 8, 10, right? For FCC it is 3, 4, 8, 11, 12, 11, then 13. For diamond cubic it is 3, 8, 11, like this. Okay, so if it is follow something like this, then we can call it, we can relate to that structure, right? So now if you try to multiply it with 2, right, suppose, so with 2, then it will be 2.7, then it will like, so it is not following any integer trend. But if you multiply it with 3, so it is like 3, then 1.39 into 3, it will be 4.17, right? So it is close to 4, then, right? So you will have to find like whatever it is that should be close to that one. So we multiply with 3, so here it is 3, 4.17, 8.314, and 11.61. Okay, so you find the approximately it is 3, 4, 8, and 11. So this follows the pattern of your FCC, right? So you can find like this. Okay, next question. A binary phase diagram of components P and Q displays an eutectoid reaction with terminal solid solutions alpha on the P rich side and beta on the Q rich side. At the eutectoid temperature, the solubilities of Q in alpha and beta are 5 and 98% respectively. The densities of alpha and beta phases are 9.5 and 2.49 gram per cm cube respectively. At the eutectoid point, the alloy has alpha and beta in the weight ratio 1:1. The eutectoid point occurs at composition. Okay, so we need to find the eutectoid point composition. The first task will be to draw the diagram, the phase diagram, right? So we'll draw this. It should be something like this, right? So see here, what are the information it is given? A binary phase diagram of components P and Q displays an eutectoid reaction with terminal solid solution alpha on the P side. So right, suppose let this one as, so alpha will be on the P side. So alpha, let us write this one like alpha, and beta on the Q side, right? So we can write here like beta, and this is the eutectoid temperature, so we can make it like this. Okay, so see here, at the eutectoid temperature, solubility of Q in alpha, that means the Q amount in alpha, it is 58%. Okay, next in alpha and beta are, and in the case of beta it is 90%, so let it be at 90%. Okay, the density is alpha and beta, so density is also given. Fine. Now see question number 50. At the eutectoid point, the alloy has alpha and beta in the weight ratio 1:1. The eutectoid point occurs on, so weight ratio is 1:1. So let this point be x. Okay, so weight percent of alpha will be, according to Lever's law, it will be, let this one x, y, z, right? So it will be, here it is alpha and here it is beta, right? So it will be yz upon xz. So it will be 90 minus x by 90 minus 5, right, into 100. Similarly, weight percent of beta will be xy by xz. It will be x minus 5 divided by 90 minus 5 into 100. So the ratio is 1:1, so let us divide both. So it will be, we can say like 90 minus x by 90 minus 5, it is equal to x minus 5 by 90 minus 5. So this will be like x equal to 95 by 2, that is 40 7.5 weight percent, and is in terms of Q, right? Okay, so option B. Now the next question, which is the tricky one. Let me add one slide over here. Okay, at the eutectoid temperature, the ratio of alpha and beta phases in the specimen observed under microscope is, right? So see, whenever a specimen is observed under microscope, so whenever we observe, so we are able to see the volume, right? And what is the actual volume? Because we can see the dimensions, like physical dimensions, length, breadth, height, right? We can't see the exact mass, right? We are not able to see, we can only see the dimension. So that's why it is said that when you observe under microscope, so that is, or that always gives you the volume fraction. Okay, so once it gives the volume fraction, so we'll have to find what is the volume amount of alpha and beta, right? So to find this volume, first we need to calculate what is the weight, right? And after finding this weight percentage, we'll have to convert this into the volume percentage. Okay, so we'll do like this. See here, because density is given for that purpose only, to find it in the terms of volume. So see, for alpha it is 9.5, alpha it is 9.5, and beta it is 2.49 gram per cc, gram per cc. Okay, now weight percent of alpha, what is this? It is 90 minus x by 45, right? It will be 90 minus x, how much it we found? 47.5 divided by 90 minus 5, 200. So this is how much, right? So it is 90 minus 47.5 divided by 90 minus 5. So it is your 50%. Yes, both we are in the same ratio, 50%. Okay, so weight percent of beta will also be 50%. Okay, so you can consider, suppose this is of 100 gram, so alpha, weight of this alpha is 50 gram, and beta it is 50 gram. Okay, so volume of alpha will be 50 divided by this density of alpha, rho alpha, that is equal to 50 divided by 9.5. So volume of beta will be 50 divided by density of beta, so it will be 50 divided by 2.49. Okay, so these are the volume, right? And in the question it is asking that the ratio of alpha and beta phases, so we'll have to first find the volume fraction of alpha and beta, because we can see the analyze the volume fraction, right? So this V alpha fraction will be volume of alpha divided by volume of alpha plus volume of beta, right? So it will be 50 by 9.5 divided by 50 by 9.5 plus 50 by 2.49. So it will be how much? See, 50, 50, 50 all are cancelled, right? So it will be like it is equal to 0.207. So see, the volume fraction of beta will be 1 minus 0.207. So it will be 0.792. So volume fraction of alpha divided by volume fraction of beta will be equal to 0.207 divided by 0.792. So it will be 0.207 divided by 0.792. It is 0.26. 261. Okay, this will be the answer. So 0.26, so it is close to this 0.25. Okay guys, so hope this will help you to prepare for your examination. Okay, this is it from my side. Hope you have enjoyed, and good luck for your examination. Thank you all.